Hello, and welcome to the Optimized MSP 430 programming across active and low power modes training. In today's agenda, we'll start by discussing what ultra low power is and why it's important to consider it in your system. Next, we'll discuss the basics of low power implementation in MSP 430. We will discuss the clock system used in these microcontrollers and why it has an impact on the different low power modes. We'll continue with a brief discussion of the features implemented in the new generation of MSP430 FRAM microcontrollers, observing why MSP430 keeps innovating as a leader in ultra-low power consumption. We will discuss some tricks and tips to optimize power consumption in your system, both from a software and a hardware point of view. And we'll finish with a discussion of some pioneering tools and resources available to you in order to keep that power consumption to the minimum. So let's start by discussing why is ultra-low power important. The global market is becoming more conscious of the environment, and so customers expect and demand greener products from manufacturers. Products that not only provide more value for the money they pay, but that are also environmentally responsible. The average consumer has 21 battery-operated devices in the home, contributing to a market of $50 billion per year. This means that 2.9 billion batteries are discarded each year and end up in landfills. And not only that, but the market is expected to grow with more and more devices connected to the Internet of Things, with an estimated 50 billion connected devices in 2020. With that in mind, designers are looking for microcontrollers that not only get the job done, but do it efficiently. And this makes MSP430 the perfect solution thanks to its power-conscious design, powerful processing capabilities, and rich set of peripherals. As leader in low power consumption, MSP430 can operate for years on a system without replacing its batteries, thus reducing the cost of replacing batteries and making your product greener. MSP430 has many features that have made it a leader in ultra-low power, including multiple and flexible low power modes from 100 nanoamps power down mode to parts which can consume 100 microamps per megahertz in active mode. A highly efficient and powerful 16-bit CPU which allows you to perform more tasks in less time. A brownout circuit which is always enabled and ensures reliable performance while maintaining ultra-low power consumption. GPIOs with only 50 nanoamps of leakage. A rich set of intelligent peripherals which can be used in different low power modes, including UARTs, which can wake up the device on reception, timers which keep counting in LPM3, ADCs which perform accurate conversions faster and efficiently, etc. A high-speed clock which is available instantly after waking up, among other many features. During this presentation, we'll see that having the world's lowest power microcontroller family is a result of continuous investments and innovations over the years. One example of this is the low leakage manufacturing process. As technology progresses, microcontrollers have been improving their processes, allowing for smaller devices at lower cost and with more integration. However, as transistor geometries continue to shrink, leakage current rises exponentially, creating a big problem for low-power applications. As a result, MSP430 not only invests to improve its processes and have cutting-edge technology, but we also invest significantly in innovative techniques to keep leakage at bay. Now, we have discussed the advantages of having good silicon, but power consumption also depends on a good hardware design. Just because you can run at 3.6 volts and you can use a 25 MHz crystal, it doesn't mean that you have to do it. And so a good design will always keep ultra-low power in mind. Finally, hardware is only half of the equation, but good firmware is just as important. And only by creating power-optimized code and taking advantage of the capabilities of the device, developers can fully leverage ultra-low power capabilities. Some of the principles which should be considered when writing efficient low-power applications are maximizing the time in low-power modes, use interrupts to control the program flow, replace software functions with peripheral hardware Some examples include using the timer to trigger the ADC or using the DMA to transfer data to UART. Power manage internal peripherals. Power manage external devices. Device choice can make a difference. More memory or a bigger device can consume more power. Some technologies, such as FRAM, can reduce power consumption significantly. And overall, write efficient code to avoid unnecessary cycles. In this section, we'll discuss some of the basics of low power mode operation in MSP430. MSP430 has three clock domains. The auxiliary clock, or A clock, which is typically a slower clock used for slower low power peripherals. M clock, or master clock, which basically sources the CPU. And the subsystem master clock, or SM clock, which is typically used to source fast peripherals. Each one of these clocks has different sources, which can be internal or external, and the actual sources depend on the MSP430 family and derivative. But the example in this slide shows the clock system for the MSP430 FR59XX. The usual trade-offs between these clock sources are maximum frequency, accuracy, cost of the area in the case of external crystals, and of course power consumption. Choosing the right clocks to source the peripherals in your application is important, as it will have an impact on what low power modes can be used. For example, by using a low frequency source for A clock, the device can go to a low power mode which disables M clock and SM clock, and it can still use peripherals, such as the timer generating at PWM. This slide shows the different LPMs implemented in MSP430. They start with the active mode, where all the clocks in the CPU are running. By disabling A clock, we can go to LPM 0 or LPM 1, and although these power savings are not the maximum we can get, this mode is still very useful when we still need high frequency peripherals, but the CPU is just waiting and doesn't need to process anything. Some of the most useful modes are LPM 2 or LPM 3, which disable SM clock. We can achieve very low power consumption in these modes, while still using a lot of the peripherals and a very fast wake up. The next mode is LPM4, achieved by disabling A clock. Since all clocks are disabled, the functionality is more limited, but we can still wake up from external events. LPM 3.5 and LPM 4.5 are available only in some devices, but developers can achieve the lowest power consumption in these modes at the expense of longer wake-up times and no memory retention. In LPM 3.5, the RTC can still wake up the device in addition to external interrupts. Different low power modes turn off different clock sources, so it's important to place needed peripherals or on clock sources that can run in the lowest power modes possible, but still support the clock frequency needed for the peripherals. This slide shows some of the basic difference between three of the most common LPMs. The wake-up times are taken from the MSP430 FR5969. Some device families are a little longer or shorter for the different modes, but this gives you an idea of the kind of differences in wake-up time you'll see between LPMs. And the important thing to remember is that developers must consider factors such as which peripherals are needed or how fast or how often the device needs to wake up in order to pick the right mode for the application. There is an important difference in the way some newer MSP430 families handle clock requests. In F1XX, F2XX, and F4XX, the clocks are disabled whether the module uses the clock or not. For example, if the device goes to LPM3, it will turn off SM clock, and all peripherals using this clock will be disabled. In F5XX, F6XX, and FRAM families, the peripheral can request a clock, keeping them active no matter which LPM is used. So for example, if a peripheral is using SM clock and the device goes to LPM3, it will actually go to LPM1 because SM clock is not disabled. The benefit of this option is that peripherals can keep working if they really need the clock, but the disadvantage is of course that the clock stays on and uses more power. The good thing is that this feature is optional and can be disabled, forcing the device to act like in the MSP430F 1XX, 2XX, and 4XX families. However, it is highly recommended to use disabled modules which are not needed in low power mode. A good tool to detect this kind of issues is Energy Trace++. This is a new tool which not only allows developers to measure current, but they can also check CPU states and the peripheral states, and we'll discuss it later in the presentation. Since energy is equal power multiplied by time, we have two vectors in an ultra-low power design that we need to attack. The first one is power that is needed for a certain task. This not only includes going to the lowest power mode available, but reducing the power consumed when in active mode. And then we also have time, and this is the time that we need to be in high power modes. This table shows an application executing 100 instructions at different frequencies every second. The faster frequencies let you go through the 100 instruction faster and go back to sleep, but they consume more current. For 100 instructions, you can see in this case that 4 MHz is the best option. Now for 1000 instructions, the case is different. With 1000 instructions, 16 MHz is a better option. At that point, the wake-up time is a smaller percentage compared to the amount of time you are active and executing the larger number of instructions. It is good to try and get a rough estimation based on your program requirements or to try different M-clock speeds to see what gives you the best current in your case. Your power profile can give you a good estimate of where power is being consumed in the application. Energy Trace++ is a good tool which can be used to check not only the states of the CPU, but all the peripherals, so it can provide a very accurate profile of your application. Optionally, developers can simply use GPIOs to check how much time is wasted in functions, or enable pins as clock outputs to check when A clock, SM clock, or M clock are active. The picture in this slide shows a capture of an MSP430 based application. Note how M clock turns on and off periodically, indicating that the device is going to a low power mode. Once we calculate the amount of time in different modes, we can calculate the average consumption. A simple estimate with a few variables can be good enough for many cases, as the one shown in this slide. But the more variables we add, the more accurate our results can be. One important consideration when using some MSP430s is the internal core voltage. Devices like the 5XX or 6XX include an internal regulator which is used to drive the CPU, and this regulator is adjustable, allowing users to increase voltage when they need to run at faster frequencies. The obvious disadvantage of running the core at higher voltages is a higher power consumption, so it's always important to select the minimum V-core possible. For example, if you wanted to run between 8 and 12 MHz, you could choose any core level higher than 1. You want to choose the lowest allowed V-core for these operating frequencies, so you would choose level 1. This will get you the best active mode current consumption at this frequency. A lower V-core level also means that you don't have to have as high of a supply voltage, which also can help save you some power. One of the most common reasons with power consumption being higher than expected has to do with GPIOs. This slide shows a simplified diagram of a CMOS inverter, but the important thing to remark is that the current consumption when VIN is at an unstable level is higher. The P and N channels are on simultaneously, creating a shoot-through current. This same effect is observed on input pins, where an input voltage between a valid low and a high can cause higher current consumption. This can happen when inputs are disconnected and thus are allowed to float, and of course when pins are used as analog inputs. In order to prevent issues with this effect, unused GPIOs should be terminated by driving them as outputs, using an internal or an external pull-up or pull-down, or developers should ensure that they are driven actively by external devices. In regards to analog inputs, Some MSP430s automatically disable the input dismiss trigger when the pin is configured for the analog functionality, while others have registers which can manually disable the functionality. The current consumption of a microcontroller increases proportional to voltage, temperature, and frequency. This relation is not always very linear, and for example, the current consumption will be higher at faster frequencies. But the milliamps per megahertz can be very different, and perhaps one family performs better at the fastest frequencies, but a different family performs better at lower frequencies. It is also important to remark that temperature effect is on a smaller scale, in microns instead of milliamps, so you will see the effect more on low power modes. In this section, we'll discuss some of the benefits and considerations when using MSP430 families with FRAM. As the world demands faster and higher performance in every application, new memory technology is needed to enable smarter solutions. FRAM, which stands for Ferroelectric Random Access Memory, provides unified memory with dynamic partitioning and memory access speeds 100 times faster than flash. In a few words, FRAM is as fast and easy to use as SRAM, but has data retention capabilities like flash. By combining this new memory with the low power DNA of MSP, we can offer lower energy consumption than ever before. MSP430 microcontrollers with FRAM, such as the FR57XX or the FR59XX, can achieve active powers lower than 100 microns per megahertz. The savings are even higher if we consider memory write operations. By having much faster write times of 125 nanoseconds compared to EEPROM or flash, which can require milliseconds to erase and write, and not requiring a charge pump since FRAM only needs 1.5 volts to write compared to 12 or 14 volts for flash, FRAM can provide write operations which are an order of magnitude lower than flash. Adding an endurance of 100 trillion read-write cycles or greater, and it's easy to see why FRAM-based microcontrollers are a great option for many applications such as data logging. To reduce wake-up losses, FR59XX uses power gating. Only modules that are requesting a clock are kept powered, but modules that are idle are only powered at retention levels, meaning that only logic specific to retaining the state of the module is powered. This helps minimizing for wake-up losses. Using modules that are in the same power domain means that the other unused domains can be powered down. The datasheet for the specific devices has a chart with the modules for the different domains. An important thing to remark is that power gating is transparent to the user. It is handled automatically by the device based on what modules you are using, so you will get the power saving advantage without any extra effort. FRAM devices use cache when making accesses to FRAM to run your program. The higher the cache hit percentage in your application, the better active power numbers you will see, and the better throughput you will be able to achieve when running faster than 8 MHz. Writing short, efficient loops can ensure optimal usage of the cache, thereby maximizing system throughput and lowering average system power. In this section, we'll discuss some power optimizations achieved with MSP430 peripherals. Developers should always take the features and capabilities of peripherals in consideration when designing low-power systems. Sometimes it can be easy to perform a task using software, but it is important to use hardware as much as we can. Some examples include using timers for delays, using special peripherals such as the CRC or the AES, or using DMA to perform automatic transfers. One example of a peripheral which can be implemented in many different ways using different low power features is the ADC. Starting with the triggers. Many implementations use software to periodically start conversions, but a lower power implementation can use timers to trigger the ADC conversions automatically, saving cycles and staying longer in low power mode. An additional feature which is not available from many suppliers is the capability to control the sample and hold time. Typically, This can be controlled by using the register in MSP430, but by using the timer trigger, you can have more control and granularity over the sample and hold time. There are a few more things to consider during the conversion, the first being the ADC clock source. ADC has options to run from the 3-system clock, which is SM clock, M clock, or A clock, but it also adds the option of a mod oscillator. This is an internal clock which is around 5 MHz and can also be used in low power mode. It's important to remark that the ADC core and the mod oscillator are automatically disabled when not converting and re-enabled when needed. Another important feature of the ADC module is the flexibility with voltage references. The ADC can run from AVCC, an external reference using VREF pins, or an internal reference which can usually be configured at different levels. Internal reference consumes more current in MSP than an external reference. However, the internal reference can be automatically turned on or off when needed. So, it depends on the application to decide which one is better. Finally, the ADC has different modes including a sequence of channels mode, also called auto-scan mode. In this mode, the ADC starts converting on a trigger, but instead of having to read each conversion and starting the next channel, the ADC can be configured to convert a sequence of channels consecutively. Once the conversion is complete, there are a few more options to consider in order to handle the data. This will be discussed in more detail in the next slides. The window comparator automatically does some of your data handling for you in hardware. Basically, it checks the ADC result against thresholds that you can configure in hardware. Based on which range the data falls in, it will set different flags and trigger different interrupts if enabled. There are 3 ranges, a high, a middle, and a low, which are set based on where the result is in relation to the thresholds. This can let you stay in low power mode unless the ADC result falls in your range of interest. This example shows what happens during 5 conversions using the ADC window comparator. The first sample falls between 2 thresholds, so it sets the ADC12 IN-IFG flag. The second sample is above the high threshold, so it sets the ADC12 high flag. The third sample set is between the 2 thresholds again, so it sets the ADC12 IN-IFG flag. The fourth sample is below the low threshold, so it sets the ADC12 low flag. Finally, the fifth sample is still below the low threshold, so ADC12 low flag is set again. Note that the flag doesn't set exactly when voltage passes the thresholds, but when the ADC converts the data. The DMA is another module which can help reduce power consumption not only for the ADC conversions, but for other functions. This module has features such as up to 7 channels, each one with configurable triggers including the ADC, software trigger, timers, AES, use key, which handles I2C, SPI or UART, DAC, multiplier, or other DMA channels. Configurable channel priority, different transfers modes, requires only 2 M clocks per transfer. Configurable block size, transfers in bytes or words, and selectable edge or level trigger transfers. This slide shows an example of a typical implementation of DMA to generate a sine wave with the DAC. By using DMA with an internal DAC found in some MSP430s, the transfers are much faster and the CPU can remain asleep in more time. DMA can be used for many purposes, but some of the most common uses include capturing data from the ADC. As discussed in previous slides, a timer can trigger the DMA, and if we add the fact that the DMA can store the result, then we can have a periodic ADC conversion which are triggered and stored automatically without any CPU intervention at all. Communications such as SPI, I2C, or UART are another very common example. For example, if we wish to send a long packet via UART, we could use the CPU to poll the transmission flag while we send 1 byte at a time. But by using the DMA, we can simply configure it and it will automatically send the whole packet without any CPU intervention. A third example is memcopy, which is usually performed by doing loop in software. Current compilers are very efficient, but if we consider that the DMA takes only 2 cycles per transfer, then we can see the advantage, especially for large transfers. DMA can be used in many other ways, which can get quite complex but also very creative. One example is using the DMA to generate complex waveforms, such as timer-based DAC. By loading the timer duty cycle registers, the DMA can generate complex waveforms without any CPU intervention. Some other examples could include using the DMA to start or stop the timer, for example, to generate a burst of pulses which are enabled only during a window of time. Maybe we can also use it to enable or disable the ADC or the reference automatically, or to generate multiple PWMs by writing directly to GPIO output registers, and many more options. We have discussed many of the features and benefits of the MSP430 architecture, but as mentioned previously, good software is just as important. So let's take a look at some software techniques to reduce power consumption. The first thing to remark is the importance of reducing CPU active time. As mentioned previously, the more cycles we can reduce from the CPU, the more time we can stay in low power mode. An important method to do this is by using interrupts. This example shows a comparison of a polling-based UART echo compared to an interrupt-based one. Perhaps this example is too obvious, since it shows a difference between a 100% CPU load versus one that is almost 0%. But in many cases the savings are not so obvious and they can be more difficult to implement. But developers should consider them if they can save some cycles. As we saw, it's important to use ISRs, but it's also important to keep ISRs as short as possible since it will allow us to go back into LPM sooner. Many developers like to do everything they need to do in the ISR, while others prefer to set a few flags and handle everything in a main loop. In reality, the best implementation will depend on a system. A simple system, which is perhaps only waking up from one periodic interrupt, perhaps could waste time in setting unnecessary flags and jumping to the main loop. But a more complex, heavily interrupt-driven system could benefit from jumping quickly to a main loop to keep everything under control, including the watchdog. And by keeping the interrupts short, it ensures lower latency and decreases the possibility to miss interrupt events. To exemplify what we have seen about software interrupts, let's take a look at an application which simply reads a voltage using the ADC, and if the voltage is above AVCC divided by 2, it turns on an LED. If not, it turns the LED off. As we saw previously, the ADC has different measures to save power consumption. This example uses an external AVCC reference and an internal mod oscillator, but it uses a software trigger to start each conversion and then wakes up the CPU after each conversion to process the results. This flowchart shows the program flow we described in the previous slide, showing what is done in hardware and what is done in software. The hardware processes can run in low power mode, but the software processes require the part to be in active mode. Since so much of the handling is done in software, the device must be in active mode a fair amount of time. When using this basic way, the ADC is using tons of power, but it's not as good as it could be. The CPU is not only wasting time triggering the ADC, but doing the comparison in software. So next, we're going to make a program that does the same basic functionality as this one in a different way, but in using lower current. This example performs the same functions as the previous one, but instead of using the CPU to trigger the ADC, it uses a timer at 100 Hz. And it also uses the window comparator to perform the comparison in hardware. In this flow diagram, we can see that the hardware is performing more functions. The hardware processes can run in low power mode, but again, the software processes require the part to be in active mode. As you can see, by using the window comparator and the timer trigger, now we have incorporated more of the functions in hardware, so we can stay in low power mode for a larger portion of the time. The functionality of both examples is the same, but as you can see, these few changes allow the MSP430 to do more work in hardware. We can take more advantage of the MSP430 low power modes, and we have much better current consumption than with lab number 1. The Optimizer Assistant can help you check the best size versus speed trade-off to fit your code in the allotted code space, but also saving the most CPU cycles that you can. The assistant builds the project automatically with different settings to help you choose the best option. Another important tool included in IDEs are the intrinsics. These are function-like operators which look like function calls, but are implemented very efficiently, taking advantage of the instruction set. Some examples include the even in range, which is used in switch case statements to tell the compiler that the parameter will be even and less than a particular number. The never executed intrinsic tells the compiler that a label is never executed, allowing the compiler to generate more efficient code. Some other intrinsics provide access to assembly instructions such as BCD add short or BCD add long, and when they can be more difficult to implement in C. For more details, please refer to SLAU 132, which is a compiler guide for MSP430. This example shows the code generated by a switch statement checking for different values. As can be observed, the assembly takes 4 instructions to do the first comparison, but the time taken for the different cases varies. With a value of 8, it takes 21 cycles to execute the corresponding instruction. Using the even in range intrinsic, the interrupt service routine is faster. Each case takes the same amount of time, and the same value of 8 takes only 10 cycles instead of 21. MATLib is a library provided by Texas Instruments which allows you to do math-heavy floating point calculations up to 26 times faster for most common math functions, including sine, cosine, square root, etc. This will let you get through your code faster and back to low power mode to conserve energy. MATLib is built into CCS v6, so it's even easier to add to your projects now. TI also has MSP430 IQ MATLib, which is a collection of optimized fixed point functions which allow you to run up to 100 times faster when executing scalar math functions. The last section of this training discusses some tools and resources available from Texas Instruments to help you optimize the power consumption of your application. ULP Advisor is a tool for guiding developers to write more efficient code which fully utilizes the ultra-low power features of MSP430. This tool checks your code against a very extensive checklist and provides notifications and remarks to highlight the areas that can be optimized. ULP Advisor is included in CCS version 6. The rules included in ULP Advisor are shown in this slide. Some of them might be more helpful to developers than others, but at the end, they all provide useful hints that can help reduce power consumption. Another very helpful tool is Energy Trace++, which not only measures and displays the application energy profile, showing the power consumption of the device over time, but it also checks the CPU and peripheral states, showing when the device is in active mode or in low power mode, or when the ADC or a timer is active. Using this tool, developers can find if, when, and where the CPU is wasting power unnecessarily, increasing the time to market with the lowest power product. Energy Trace++ can use MSP-Fed or use EasyFed included in the Launchpad for FR5969. and it's supported in the latest version of CCS and IAR. It is important to remark that there are currently two versions of this tool, Energy Trace and Energy Trace++. Even though both versions can measure energy and power, Energy Trace++ can also check the CPU and peripheral states. Energy Trace++ is supported in some devices like the FR59XX, but Energy Trace can be used in all MSP430s. When it comes to low power, MSP430 offers an ecosystem which is second to none. We have discussed some of it during this training, but for more information please refer to the links shown in this slide. Thank you for your time, and we hope you keep enjoying developing your lowest power applications with MSP430.